In this video, we present our work, LetsMap, Unsupervised Representation Learning for Label-Efficient Semantic Bird's-Eye View Mapping. Bird's-eye view maps have become an integral part of various autonomous driving pipelines due to their feature-rich yet computationally efficient representations. Existing approaches follow a fully supervised training paradigm and thus rely on large amounts of labeled bird's-eye view data. However, labeling bird's-eye view data is cumbersome and extremely expensive. In this work, we address this limitation by proposing the first unsupervised representation learning framework for generating semantic bird's-eye view maps in a label-efficient manner. To this end, we split the task of semantic bird's-eye view mapping into two constituent subtasks, namely geometric modeling, which follows an implicit field formulation, and semantic understanding, which we design using a novel temporal masked autoencoder. We then fine-tune the model for the bird's-eye view segmentation task using only a small fraction of labels in the bird's-eye view. The core idea of our approach is to leverage sequences of multi-camera RGB images to learn strong geometric and semantic features following a label-free paradigm. The pre-training stage learns to model the scene geometry by enforcing scene consistency over multiple views using the photometric laws. Parallelly, it encourages the model to learn the scene representation by reconstructing a masked input image over multiple time steps using the reconstruction laws. We designed the task of scene geometry modeling using an implicit field formulation wherein the main goal is to estimate the volumetric density of the scene. We supervise the implicit field using spatiotemporal images obtained from cameras on board the autonomous vehicle. We reason about scene occlusions and disocclusions by following the idea of image condition nerves and using forward-backward image warping. Finally, we supervise the geometric pathway using the photometric laws between the real and warped images. The semantic pathway aims to facilitate learning of holistic feature representations for various elements in the scene in a label-free manner. To this end, we first mask out random patches in the input image and pass it through the backbone and adapter modules to generate a uniform voxel grid. We then multiply the resultant voxel grid, encoding semantic information, with the occupancy voxel grid from the geometry pathway to obtain a voxel grid that accounts for both the semantic and geometric knowledge of the scene. We then encourage the network to generate pixel-wise predictions for each of the masked patches. We also exploit the temporal consistency of the scene by reconstructing the RGB images at future time steps using only the masked RGB input at time step T0. The aforementioned two steps of scene geometry learning and scene representation learning make up the initial unsupervised pre-training step. Once pre-training is complete, we set up the network for fine-tuning by disabling image masking and discarding the RGB reconstruction head. We fine-tune the network on semantic bird's-eye view mapping by training the model on a fraction of bird's-eye view ground truth labels. We quantitatively evaluate the performance of our unsupervised representation learning framework on the Kitty 360 dataset. In this plot, the blue bars represent models trained using 100% of bird's-eye view labels. The green bars show models trained using only 1% of bird's-eye view labels, and the red bar represents our approach. We observe that our approach, LetsMap, outperforms the baselines trained using 1% of bird's-eye view labels by 2.02 percentage points. On the new scenes dataset, we observe that our approach outperforms Semantic BEV, trained using 1% of bird's-eye view data by 3.63 percentage points. Here, we analyze the impact of our unsupervised pre-training strategy by progressively increasing the amount of bird's-eye view labels from 1% to 10%. In this plot, LetsMap with our pre-training strategy is shown using a solid red line. LetsMap without pre-training is depicted using a dashed red line. The baseline sky eye is shown using a solid blue line, and Panoptic BEV is illustrated using a dashed blue line. We observe that our approach significantly outperforms both sky eye and Panoptic BEV by a large margin across different percentage splits. Here are some qualitative results from our model. For more information about our work, please visit the project page using the URL shown here. Thank you.